In this video, we're going to work through this chunky exam problem on high derivatives as parametric curves. So do pause the video and try this one for yourself. Okay, the positive variables y and t are related by y equals a to the t. A is a positive constant. By differentiating ln y with respect to t, show that dy by dt is a to the t ln a. Okay, so this is just a sort of fairly standard implicit differentiation here. So I'm going to start by just taking ln of both sides. So ln y equals, and then ln of a to the t is t ln a. And now I can differentiate with respect to t implicitly. Differentiating this with respect to t gets me 1 over y dy by dt. And differentiating this side with respect to t, the t just goes and I get ln a. Therefore, dy by dt is just y times ln a. But what was y? Well, going back to the original question, y is a to the t. So we've got a to the t, ln a. Okay, we're done now with part A. Part B, write down the second derivative. Now, 1 mark, we should be able to do this without any work. Well, the observation here is that differentiating a to the t with respect to t, well, what did it do? We just multiplied by ln a, which is a constant. So if we're going to differentiate this one now, well, the effect is just we multiply by ln a again. So it's a to the t multiplied by ln a squared. It's a little bit like saying, let's say I was differentiating e to the kx. Well, dy by dx is k e to the kx. And if I differentiate it again to get the second derivative, it's, well, the effect of differentiation was just multiplying by k. So it's, once again, it's just k squared e to the kx. It's not identical to that, but it's the same kind of idea. I observed that differentiating a to the t just resulted in multiplication by a constant. So if I differentiate again, I just multiply by the same constant again. Okay, on to the next part of the question. So a curve has parametric equations x equals t to the a and y equals a to the t. Okay, so we've already done our work with that y equals a to the t. Find d2y by dx squared in terms of a and t, and show that when t equals 2, the second derivative is that. Okay, so this is a bit of a beast, this question. So let's start with dy by dx. So dx by dt, well, okay, differentiating this with respect to t, well, that's just like that's just a polynomial. So that is a t to the a minus 1. That's fine. And we already know that dy by dt is a to the t ln a. So that means that dy by dx is simply this one divided by this one. So a to the t ln a divided by a t to the a minus 1. Okay, on to our second derivative. So what do we need to do here? We need to differentiate this with respect to t, and then we need to multiply by dt by dx, which is going to be the reciprocal of that. So differentiating this with respect to t, well, this is going to be a quotient rule. So vu dash. Okay, here's v, a t to the a minus 1. Now u dash, we know how to differentiate a to the t ln a. We did it in the previous question. We did it here. Its derivative was a to the t ln a squared. So u dash is a to the t ln a squared. So there's vu dash. Now minus uv dash, so let's get u in, a to the t ln a, and v dash, well, this is polynomial, so I just need to multiply by the power, and the power drops by 1 down to a minus 2. all over v squared. So squaring each term, that's a squared. And then squaring t to the a minus 2 just doubles the power. T to the 2a minus 2. Now I need to multiply through by dt by dx. That's the reciprocal of this. So that is just dividing by that. In fact, I'll just pop that down here then. So I'm multiplying by another a and t to the a minus 1. Okay, let's see what we can do. Well, actually, you know what? We don't need to do anything just now because we need to set t equal to 2. So let's go ahead and do that. So when t equals 2, I've got a, well, let's try and do the a's together. I've got a times a to the t, that's a to the t plus 1. So a to the 2 plus 1 is a cubed. Then I've got 2 to the a minus 1. Then I've got ln a squared. Now I've got a squared here. I've got ln a. Oh, I've got another a there, so that's a cubed. Then I've got ln a. Then I've got a minus 1 and 2 to the power of a minus 2. All of that over a squared times a is a cubed. Great, the a cubes are going to cancel, that's good. Then I've got 2 to the power of, well look, let's add the powers here because it's t to the that times t to that. So in total that would be t to the power of 3a minus 3. So that's times 2 to the power of 3a minus 3. Right, looks bad, but the a cubes are gone. And all that's left in the denominator is this power of 2. So let's just divide the powers of 2 up here by that. So 2 to the a minus 1 divided by 2 to the 3a minus 3, I can just subtract powers. So a minus 1 minus 3a minus 3 is 2 minus 2a. So that is 2 to the power of 2 minus 2a. I've still got my ln a squared. The a cubed's gone here. I've still got my ln a and my a minus 1. And then here the power there, so a minus 2 minus 3a minus 3 is 1 minus 2a. So that's 2 to the power of 1 minus 2a. Okay, we're getting pretty close to here. And I think we've just got to force the issue, which is to say I want there to be a 2 to the power of 1 minus 2a factored out, and I want there to be a ln a, so let's pull that out as well. So pulled out from each of these, what's left? Well, from this one, so the power here is 1 more than it is there. So I've got a 2 from this one, 2 to the 1, and I've got a ln a. Now from this one, I've got all the 2's I want and the ln a. The only thing I don't have is the minus a minus 1. So that's minus a plus 1. And look, I think we're done. We are done. 2 to the 1 minus 2a. There's the ln a that I've got here. And then I've got 2 ln a minus a plus 1, just in reverse order. So we are done. So not so bad after all. Anyway, if you did that one yourself first, well done. If not, I hope it all makes sense. And I'll see you in the next video.